Hello, I'm Masaki Hada. I started my research career in University of Tsukuba from 2019. So our team is quite new, and the first student joined in 2020. So we have currently 4 master students and 2 undergrad students. Our team develops and applies ultra-short pulse electron source to observe dynamical phenomena with atomic spatial resolution. We call it a molecular movie, and literally we can see the atoms or molecules in action.
Time and space are connected. In general, bigger matters move more slowly. At our fastest, we humans move on the millisecond time scale. When matter gets smaller, it moves faster and faster. For example, the atoms and molecules on the sub-nanometer scale typically move on the sub-picosecond time scale. On the sub-picosecond timescale, atomic or molecular motions in a state of thermal non-equilibrium can be observed. Exotic atomic or molecular motions are our research target. To directly observe atomic or molecular motions in materials, we use ultrafast, time-resolved electron diffraction measurements. In the time-resolved electron diffraction measurement, a sample is excited by optical pulse, and the atomic or molecular structure of the sample under photoreaction or the non-equilibrium photoexcited state are monitored by the electron pulse through diffraction. The de Broglie wavelength of an electron is 1 to 10 pm, which is smaller than the typical atomic scale. Such wave particles are known to interfere with or diffract off of matter, providing detailed structural information.
My name is Yajima Ataru. I am a first-year master's student. I am developing a new system for time-resolved electron diffraction experiments. It will observe 3-dimensional atomic and molecular motions. I am learning mechanical design, vacuum engineering, and laser engineering. I'd like to use these things and work as an engineer to develop analytical instruments in the future.
Our work is separated into 2 parts. One part involves developing and upgrading ultra-short pulsed electron sources. This part is tough, but it is a lot of fun. Our members create measurement setups from scratch. First, we make technical drawings of the setup. After making the technical drawings, we build the setups. Developing time-resolved electron diffraction setups requires expertise in several areas. First, the electron beam travels in high vacuum, so we must understand high vacuum and electron optics. The electron beam is accelerated by the strong electrostatic field. Therefore, we must understand high voltage. Additionally, time-resolved electron diffraction requires the use of an ultra-short pulsed laser. Thus, we learned about optics for ultra-short pulsed lasers. We also learned a program to automate the setups. Based on our combined knowledge in each of these areas, we developed the setups.
Hello, I'm Yuri Saida. I study structural dynamics of materials using ultrafast time-resolved electron diffraction. I focus on the organic liquid crystal that melts by photoirradiation. At first, we don't know why it can melt by photoirradiation in molecular scale. So I performed ultrafast time-resolved electron diffraction measurement and simulation to support the experimental result. I found molecules change their conformation by light, and it is a reason of melting. With ultrafast time-resolved electron diffraction, we can connect microscopic phenomena, structural dynamics of molecules, and macroscopic phenomena and material characteristics such as melting, conductivity, luminescence, and so on. I think that the knowledge of structural dynamics will contribute to developing attractive new materials.
The other part involves applying ultrafast, time-resolved electron diffraction to molecules and materials. We have 2 ultrafast, time-resolved electron diffraction setups at the University of Tsukuba, and one currently being developed at the Tokyo Institute of Technology under a collaboration work. We are working on the photoinduced ultrafast structural dynamics of all types of materials, inorganic materials, organic materials, and carbon materials are our targets. Samples come from both domestic and international collaborators. The time-dependent electron diffraction patterns of samples are captured by our developed machines. The electron diffraction patterns are analyzed using numerical software, and these are compared with theories or the results of simulations to understand the atomic or molecular motions in the materials.